have Yampolsky from University of Toronto, Mississauga, will tell us how to use it. Take it away, Mike.
Okay. Thank you for inviting me. So what I would like to do, at least to some extent, I would like to discuss the theoretical obstacles to numerical modeling of dynamical systems. And somehow, ever since the dawn of computers, people have been trying to model dynamical systems in various circumstances. And apart from purely practical problems, there are some theoretical limitations to what one can and cannot model. And they are related. So that I would like to give you some gist of mathematical questions that come up. Right, but first, just as an example to keep in mind, everybody's, I guess, favorite example of difficult to model dynamics comes from weather prediction, right? I mean, as we all know, weather forecasts looking a few days in the future tend to be quite unreliable, right? And this is perhaps the first famous example of what's colloquially known as chaos. So the story goes like this. In the year 1961, if I'm not mistaken, a meteorologist by name Lawrence was considering some really basic numerical simulation of some weather patterns. And these are the Lorentz equations. I mean, this was really basic. We were talking early 1960s. So a three-dimensional system of nonlinear differential equations, very mildly nonlinear, quite famous. This is known as the Lorentz system. So Lawrence, at least the story goes like this. Lawrence tried to save some time since the computations were very time consuming on the computers of the era. And he needed to run the simulation for some extended period of time. He tried to save time by saving some intermediate values. So then when he would have to repeat the calculation, he could just plug in the intermediate values and pick up from there. And to his amazement, what the repeated simulation gave numerical values which were completely different from the original one. And now, I mean, the culprit is easy to point out. It's the round of error that occurred when the intermediate results were saved. And this is a thing that we now know as chaos, the situation when a small change in the initial conditions, so that would come in practice either from a measurement error or from a numerical round of error, would introduce a large error into the calculations, right? So the error would propagate at an exponential rate with time. So the calculations, once you run them for some extended period of time, would be completely unreliable. And I mean, in here, I'll just run the simulation for some initial values. Of course, this is a three-dimensional system, and I only have a two-dimensional plane. But you'll forgive me, this is a two-dimensional projection. So the point is that if you take two nearby points, so let me just click at two nearby points, then you will see quite rapidly, I hope, that of course there's continuity, so the trajectories have to stay close for some time, but then they will diverge and start doing something different. And this already happened. This just happened, you see? So there was a big difference introduced already at this stage, and this will repeat. Right. So this is a two-dimensional projection of a three-dimensional shape, which is a famous Lorentz butterfly, and somehow this one example popularized, you know, chaos.
Sorry, so this is two-dimensional.
This is three-dimensional, really. It's supposed to be three-dimensional. It's a two-dimensional projection. There's a slice here.
So I just want to check if I understand this correct. So are there fixed points inside those?
There will be fixed points, right? There will be fixed points that there'll be periodic trajectories. They are repellent in this particular example. But if you take a typical trajectory, then it will eventually trace out a rather complicated shape. It's known as the Lorentz butterfly and so on. I'll let this run for a bit. I would like to make a point that even though even such basic weather simulation is really hard, and imagine, you know, the actual weather forecasts nowadays take into account a lot more than 3 variables, and it's still very hard. However, we do get predictions in the forecasts, and not only we get them, they're even sometimes correct. The language we get them in typically is non-deterministic, right? I mean, you would have something like the probability of rain, you know, day after tomorrow is 40%, right? What does this actually mean? I mean, why are probabilities involved? I mean, and also, why is the prediction framed in such a way? I mean, either there will be rain or not, right? I mean, the answer should, it seems that the answer should not be given in probabilistic terms. I mean, the title of my talk, of course, is a giveaway. The reason the answers are given probabilistically is because they're results of Monte Carlo simulations, right? One doesn't ever try to actually calculate predictions exactly, right? Because of this. So the difficulty will be that your measurement error in the initial conditions or the computation error will very quickly render any kind of exact prediction useless, right? But the hope is that what you can do instead, you could try rerunning your simulation a lot of times with different initial conditions, and you could look at the statistics of the outputs. And in fact, this picture, I mean, I wanted to keep it running because I would like to make a point that in here, for this particular system, the statistics of the orbits will actually be the same. So even though they will be doing different things, very different, I mean, at this point, they probably have completely forgotten about each other. They're doing different things at the same moment of time. Their statistical distribution is actually the same. In this case, it is the same. It's a theorem. Okay. What is also the same is the limit in shape that you will see, right? So it does make sense. I'll answer in just a second. Let me just finish the sentence. So the point is, what does make sense, or at least what seems to make sense, is to try to make statistical predictions about long-term limit in behavior, right? And in that sense, we are generally quite successful, right? With a high likelihood the next month is going to be colder than this one, right? I could probably slap a probability on this, and I'll probably be right. Yeah, sorry. So what's your
basic question? My statistics do just see introduction.
Yeah, so I will make it exact. So in fact, I could do it right now. So here, so this is, can I write here? Is that all right? Yeah. So let me look at discrete time dynamics rather than continuous time dynamics, which is just to make things simpler. And also because any numerical simulation is discrete time dynamics anyway, because you're using some discrete time numerical scheme to approximate this, right? So we'll have some map which describes the evolution of our dynamical system at one tick of the clock from some omega, which is somewhere in, say, Rn to Rn, right? And I would like to know the long-term statistical behavior. So what I'm going to do, I'll pick at random k initial conditions. So x1, x2, etc. xk. I'll run the dynamics for some large time for each one of these, right? And I'll look at the full-on sum, 1 over k, because I want to take the average, 1 over n. This is how long I'm going to run the dynamics. Sum j goes from 1 to k. I goes from 1 to, well, I should do from 0, from 1 to k, and here from 0 to n minus 1. And I'll do f iterate at k times at xj, I times at xj, and I'll put a delta mass in there, right? So I'll just look at the distribution of the points in the orbit of each one of these. I'll take the averages. So it's an average of Birkhoff averages, if you would like, you know, fancy terms. And I hope that as k and n go to infinity, when they become large, that this converges, right? That this has a limit, which is my limit in distribution. So that's the sense in which we talk about the limit in statistics. And then, well, and if this recipe works, then I would hope that if I take a large k and a large n, then I will get it, and I calculate the finite sum. So I'll just run this for a long time for some choice of initial points, then this will give me a good approximation of the limit. And then I'll be able to say with what probability it will rain. Okay, that's the Monte Carlo method. It has a funny history. So it was invented by Stanislav Ulam when Ulam was working on the Manhattan Project. And so the story goes that Ulam got sick, ended up in a hospital for a few days, got bored out of his mind, and started to play solitaire. And then decided that he was interested in the probability of winning at solitaire, finishing solitaire, right? So, but that, of course, that's just too hard to calculate. And then he had the idea that if he just played a lot of times and he kept track of how many wins and how many losses he had, he would know. And then he had the idea that he and von Neumann could use this for modeling the neutron diffusion on von Neumann's new computer. And in fact, and he wrote a letter to von Neumann, which was, of course, classified as top secret and was declassified sometime in the late 40s, and at a conference at which Monte Carlo method was declassified. And in fact, if you look at the Wikipedia, so this is my final bit. So this is a Wikipedia page on Ulam. So there's a blurb on the Monte Carlo method, and there Ulam is holding an analog Monte Carlo simulator called the Fermiac, built by Enrico Fermi, who, after listening to Ulam and von Neumann's idea, actually built an analog machine to simulate neuron diffusion. So there. Okay, good. So let me now switch off the screen, unplug this, and get serious and tell you about some theorems. Okay, let me make some basic definitions, which will help us. So let me say that, so I'm still in that setup, right? I'm still looking at a discrete dynamical system defined on some domain in a Rn, for instance, right? And I'm interested in the limit and statistical behavior. So let me say that mu is a physical measure if the limits of Birkhoff sums listen, this will never mean a power. This is an iterate, right? In my talk, there'll be no powers unless otherwise specified. And I want to always remember to draw the little circle. Yeah.
So for example, in weather, I have to make f size smaller as well, right? Because you don't want to know time. You want to protect it.
Well, I mean, it's a fair question. So yeah. So you need obviously you need to say a few more words if you want to model continuous time as opposed to discrete time dynamics. But in practice, what one does really is take some high precision, say double or quadruple precision discretization of your thing. Never think about this again, right? Just use that and work with that finite precision. But in principle, you could keep increasing the precision for everything. This is now going to be math, right? So for a bit. Yeah. So let's not talk about.
I'm just trying to why you propose and then doing.
Yeah. So I'm getting there, right? You're just a little bit ahead of. Yeah. So So if. Right. So if this converges to mu for x in some set of positive measure. Positive Lebesgue. So in a sense, physical measures are the ones that the types of limit in statistics we can actually observe if we pick the initial values at random, right? If this is positive, then with positive probability we'll pick something like this, and then so that's at least the justification, right? That's a physical measure. So of course, right, and let's say that the set of all such x is the basin of mu. Such a measure may or may not be unique, right? You could have a lot of them. There are examples of, maybe I should also say, so this is a definition. And here's another definition. An ergodic physical measure is known as SRB measure. SRB stands for Sinai-Royal-Bowen if you don't know what ergodic is, don't worry about it. It just means that this cannot be decomposed. You cannot break this up into physical measures on, different physical measures on smaller sets. No, F is not measured. So, right. Okay, so you could have simple dynamical system. So you should think about it this way. So answering your question, if there are finitely many SRB measures whose basins are everything, which is sort of the whole, then such sampling, assuming K is large, should catch all of the basins with high probability and then in the right proportions, and then you will have your answer. If it's unique, even better, because then you don't need to sample a lot of points. You just pick a point at random, and with probability 1, it's in the basin and you're done. But it doesn't have to be unique and there don't have to be finitely many. There are examples of polynomial maps of degree 2 in 2 dimensions due to Newhouse from 1970s, for which there are countably many attractant basins, attractant periodic orbits. So in each one of those, of course, corresponds to its own SRB measure. So there'll be a lot of them. But that's not necessarily an obstacle to Monte Carlo, right? Because if you think about it, you don't really care what happens on small portions of the phase space, because you're unlikely to find yourself there. So as long as, most of omega is covered by a finite collection of basins of SRB measures, you're in good shape. Okay, so that's a mathematical setup.
You're not assuming full measure or anything. Yes.
Yeah, so no, I'm not assuming that the basin is a full measure, and it won't be if obviously if there's more than one, but in the situations that we'll look at, it will be, and there will be only one, and things will already be pretty bad. Okay, so I'm going to talk, so the setup is clear, right? Here's another bit of terminology. Sometimes you call this support of an SRB measure is an attractor. It's one way of defining an attractor, one way of defining a limiting object or orbits on some large set of initial conditions. There are other, right? You could look in the limits in purely topological sense. And again, in the examples I'll look at, all of those definitions are the same and the attractor will be unique. Okay. Mostly, this is not entirely true. This has been recorded, right? So I can't really lie. Okay. Edit it out. No, it's right. I already said it's not entirely true, so it's fine. Okay, so now I want to talk about what cannot be computed in this setup, right? What the theoretical obstacles are. So I have to talk a little bit about theoretical computability and models of computation and so on, right? Okay. So this is good. I can erase this for now. Okay, so computer scientists, when they talk about models of computation, they typically talk about Turing machines, right? In my experience, everyone has seen the definition of a Turing machine and no one actually remembers what it is. And that's fine, because a Turing machine is provably equivalent to a program running in your favorite programming language, right? So this is just a computer program in the sense that the computational power of this is the same as a computational power of a program written, I don't know, in Python. Right? The only thing is when we're talking about computations using Turing machines or program in Python, at least for the duration of this talk, we don't limit the resources that they need. So if the program needs more memory, you just throw it in. Right? And I will interchangeably use the words a Turing machine, a program, an algorithm. Right? They all mean the same. Okay, so definition of Turing machine goes to the famous paper of Turing from 1936. So this is before computers actually appeared. And the the main subject of the paper was to discuss computability and non-computability of real numbers, which is good. I mean, a real number is a continuous object, and we'll talk about computability of sets and measures, so that's good. So let me give you a definition. So Turing's definition was that X in R is computable if there exists a Turing machine, let's call it M for machine, which takes one input, and this input is a natural number n, and I'll draw this curly arrow to indicate that it's been given to the algorithm, and then the algorithm will give an output, say dn. Now, it's an output of a computer. If you like to think that your computer thinks in binary, then this is a dyadic rational, just a finite string of bits. All right, so dn will have the property that mod x minus dn will be less than 2 to the minus n. Now, 2 to the minus n is entirely irrelevant. It's just pretty, you know, good to the nth bit. I could instead put here, say, 1 over n. And it's or 1 over n squared. It doesn't really matter. It's an equivalent definition. If you can do one, you can do the other. So a computable real is the one for which you can give a constructive Cauchy sequence, a Cauchy sequence with a constructive bound on the remainder term. And there's a couple things. Can I actually see a show of hands? How many of you were familiar with this 5 minutes ago? Okay, so some of you know more than I do, so that's good. So good. So here are a couple observations for those who are not previously familiar with this. Okay, first of all, there are only countably many computable reals. So let me maybe denote by R sub C computable reals. So first of all, R sub C is countable. And that's very easy to prove. There are only countably many programs you could write in Python. Secondly, all the numbers that we know are computable. Because they all come, you know, E, pi, whatever, the Feigenbaum constant, all rationals, doesn't matter. They all come with an algorithm for the definitions are constructed. So, but Turing gave an example of a non-computable real, and to give an example of a non-computable real, you need an example of uncomputable problem, right? A problem that cannot be solved on a computer, and it's a problem well known to practitioners. So imagine that you have written some code, managed to get it to compile without errors, and you do a trial run, right? And it runs and runs and runs and runs and runs and runs and runs. And at some point, you have to make an executive decision. Is it still doing something useful? Right? Or has it gone into some sort of an infinite loop and you should just put an end to this? And that turns out to be an algorithmically unsolvable problem. So this is known as a Halton problem, but the Halton problem is not the problem, it's a theorem. So the Halton problem there does not exist a Turing machine, M, which as an input takes a different machine. So it's just a program that reads another program and then outputs 1 if M1 halts and 0 if not. So if you've never seen this before and you're a student and you get really bored with the rest of my talk, I suggested to do this as an exercise. So the existence of such a thing would lead to a paradox, which is like the Barber paradox, right? Okay, so, but once you know that this thing doesn't exist, it's then you have this definition and you Turing, then you can give an example of a non-computable real. And you do it in the following way. You order all possible Python programs, say lexicographically. I mean, you just take all sentences that could be written in Python alphabet and you list them. So you have all possible programs. Of course, most of them don't run, but that means they halt by definition. Some of them run. And then you define the Halton predicate. Right, so you define P of n, which is 1 if Mn halts and 0 if not. And then you write the number alpha, which is the sum of P of n times 3 to the minus n. I'm taking 3 rather than 2 because of this in my definition. I don't want an ambiguity in the binary description of this number. Okay? So being able to compute this is equivalent to being able to solve the Halton problem. And if I want, you know, for obvious reasons, I mean, if I can solve the Halton problem, then to get a good approximation of this, I just take the first k machines. For each one of them, I know the Halton predicate. And that gives me a good approximation. And vice versa. Something absolutely terrible. Okay, so not so terrible. Okay, good. All right, now we're going to talk about computability of measures, and that's not so different. I could talk about, you know, you could define computability of sets using the same idea, computability of measures. So I could talk about computability of measures using some dense set. So all my measures will be probability measures. So they all live in the unit sphere in the space of measures. And I could just take some representative dense set, like finite combinations of delta masses at rational points, for instance. And I could use that you know, I could do something exactly like this by asking that my algorithm produces an output in that set, which approximates my measure. But as usual with measures, it's easier to give a dual definition, right, involving integrals. So here's a definition with measures. We'll simply say mu is computable if you can integrate against mu with numerical, with a finite precision. So mu is computable if there exists a Turing machine. And let's just pick some set of test functions. I don't care what they are, one Lipschitz, piecewise linear, whatever. So I, k will be my test functions. Maybe I is bad here. Phi k test functions. Turing machine M, which now takes two inputs. So M takes N, that's going to be the precision of computation, and K, which will tell you which integral this thing which integral needs to be computed, and it outputs I and K such that the distance between I and K and the integral of phi k d mu is less than 2 to the minus n. There. That's a definition. Okay. Now I'm almost done with abstract definitions, and I could formulate some theorems, but I need to make one more important point. So you have this function here, which, you know what? Actually, let me postpone that. Let me do it in a more specific setting. Let me tell you about the dynamical systems that we are going to consider. Okay, so those are everyone's favorite example of nonlinear dynamics, also the simplest nonlinear dynamical system that you could consider. It's a quadratic map of an interval. So the family that I'll specifically look at would be f sub lambda of x, which is 4 lambda x 1 minus x. Lambda is in 0, 1, and x is in 0, 1. 0, 1. A graph of such thing is a flipped parabola, and as long as the vertex is at a half, right? The highest point here is lambda, and as long as lambda is between 0 and 1, this maps 0, 1 to 0, 1, so you can actually iterate, and that's good. Okay, this is you know, this is as simple as it gets, and in dynamics, this is everyone's favorite model family, both in one real and in one complex dimension. And let me tell you a little bit about this family. It's really nice. So from the point of view of limit and behavior. So this is logistic, yeah. Logistic equation, that's right. I shouldn't have read, well, okay, too late, that's okay. I can always write it again. Okay, so here is a theorem, for instance. Which is mostly due to Lubitsch. That for almost every lambda, there exists a unique SRB measure whose basin is all of 0, 1. Okay. I can also tell you about the attractors of such maps, and it turns out that in whatever sense you want to define the attractor as a topological limit for a generic initial condition, or measure theoretic limit for almost every point of the support of the SRB measure, for almost every lambda, this answer is going to be the same, and it's going to be unique. And in fact, it can be described in some fairly precise way, but let me not go into that unless I have some time to spare. Okay, so this is as good as it gets in that sense, right? We'll call this thing mu lambda. Okay. Now, another thing to keep in mind is that it's not so difficult to find, well, to define what the support of mu lambda is in this case. So the support of mu lambda happens to be the omega limit set of the critical point of 1/2. So the omega limit set is just the set of limit points of the orbit. Okay. So the limit and behavior of this will determine where the measure will be supported, and then everything else will just converge to that. And that's the trap. Okay, now I'm going to talk about computation of any questions so far, by the way? Yeah. No, it's an uncountable set of zero measure, and there is, I mean, it's a fairly good understanding of what bad lambdas are like, right? Correct. Correct. Yeah, but that's sort of the game we're playing, right? You're given your dynamics as a black box essentially, right? And you want to run something like Monte Carlo to get sensible statistical predictions for long-term behavior. I mean, if you knew what it is in advance, that would not be fun. So that's what we're playing, right? Okay, so I'm going to give you a theorem, but before I give you a theorem, I have to remind you that to compute the measure, we do what? We take n, k, and then we output I and k such that the I and k is a pretty good numerical approximation of the integral. Okay, it's sort of silly to expect our computer program to do some computation for f lambda like this if we don't tell it what lambda is. Right? So we have two options. We could either, lambda is a real number in 0, 1. And as we know, most real numbers are uncountables, are uncomputable. So you cannot write a subroutine into your computer program, which will spit out lambda. So we have two options. We could either limit ourselves to computable parameters. That's one possibility. Or we have to input lambda externally. Then we don't have to worry about this. I'll go for the second option, maybe for the sake of definition. So that means that this machine can read lambda. You could just ask, so the technical term for this is an oracle for lambda. The oracle really here, it's a very misleading definition. It's not the command that's the oracle, it's the user, it's me. So I wrote this program, the program asked me input lambda, please. And I do it, and maybe the program will need to query some more digits along the way, to make it a bit more precise, but I'm the oracle. And then after some time, it will give me the answer. That's sort of how most of these programs are written. I mean, the parameters can be put in. Sometimes it makes sense to write a program for a specific set of parameters. And in that case, you need them to be computed. Okay. All right, so let me give you two theorems. So the first one is joined with Cristobal Rojas from Santiago, Chile. And the theorem is that there exists an uncountable set of lambdas such that, first, well, maybe I should call this set something. I don't know, S. Such that for any lambda in S, there exists a unique S or B measure mu lambda whose basin is 0, 1. And moreover, the support of mu lambda is the omega limit set of the critical point. And mu lambda is not computable. And before commenting on what this means in practice, let me also state a refinement of this. Well, it's not quite a refinement because here we're talking about an uncountable set, so it definitely contains some non-computable values of lambda, but we also have a constructive counterpart of this with Pierre Berger from Paris, Cristobal Rojas from Chile, and yours truly, in which we just say that there exists computable lambda such that. Okay, so you cannot finesse this problem by restricting yourself only to lambdas that could actually be written into the algorithm. Okay, so what this means in practice is that for such lambdas, first of all, what this means in practice is that computation of limiting statistics is hard, even when limiting statistics exists, right? So one has to be careful at the very least when applying things like Monte Carlo. The convergence is not guaranteed in any sense, but the situation is worse than that. I mean, this thing does converge here. Right? It has a limit, but you cannot compute it. And it doesn't matter, something being non-computable means that it doesn't matter which algorithm you'll write. It will make a mistake. It will go wrong. And another thing is purely philosophical level. It has to go wrong in such a way that you will not know. That's important because otherwise you could tell the wrong answers from the right ones, and then you'll be able to compute. And so in that sense, they're truly hopeless. So you lose with this. You lose in Monte Carlo, you lose in general. You will not be able to compute this. Okay, any questions about the theorems? There is a, yeah.
It looks like one theorem contradicts countable and
No. So there exists an uncountable set. So certainly in here, most lambdas are not computable. But an existence of even a single computable lambda is not guaranteed by this theorem. This theorem tells you that there exists at least one computable one, which this is also true. Okay. Correct. I didn't. That is correct. So this family is too nice. This should not be typical, right? So this should not happen for a typical lambda. No, no, but I would guess that this is true in this family. So the really interesting question is I mean, this is a very simple family, right? So the really interesting question is how bad things get when you look at more complicated dynamics. So for instance, what happens in dimension 2? In dimension 2, if you take quadratic polynomial maps, then there are all sorts of interesting difficulties. There's a Newhouse phenomenon, for instance. So the set of limiting statistics in general is more rich. And there you could, I don't know what to conjecture. I don't know if this is a measure zero phenomenon. I don't know if it's topologically generic that a limit in statistics is computable. It's pointless to ask whether SRB is computable because it won't be unique in general, but you could still ask if the limit in statistics is computable. I don't know. The phenomenon, the proof is sufficiently robust somehow so that it seems that it would translate nicely in higher dimensions. I don't know, depending on the interest, I could maybe spend 5 minutes to give you an idea of how one could prove such a thing. But before I go there, does this answer the question? Yeah. So I think this is not, so typically this doesn't happen in this family. And I don't know if this could happen for a large set of lambdas in more complicated families. And I think this is an extremely interesting and a very practically important question. Mm-hmm. Definitely. We've been looking at the genericity of this this is one of the things that we've been thinking about. Okay. Mm-hmm. So yeah, one can look at attractors as sets and ask similar questions there. And the situation is nicer. So we have a theorem with Cristobal, which I'm not going to put on the board. I'm just going to say it, that the attractors in this family are always computable. Okay. However, they could have arbitrarily high computational complexity. So they could be computable, but the computational cost of getting a finite precision approximation of those sets could be as high as you like. So in practice, they would be computable in theory, but not in practice, right? But in this case, it's just not computable even in theory. Okay. Should I don't know. What do you think? Should I stop and let people go if they want to, or should I spend 5 more minutes on telling you how one could construct this? What's the protocol? How much time do I have? Okay, yeah, so might as well. So let me give you just a little bit of an idea. The idea really is that we have too much flexibility in constructing a limiting measure, even in a simple family like this. I cannot really make it arbitrary, but I almost can. So there is a construction which allows me, when taking some specific Cantor set that moves nicely with lambda, and put in weights, so making that the support of mu lambda, and put in weights on that Cantor set however I like. That's too much flexibility. That's like the same kind of flexibility as defining a real number. You could just put whatever values you like for the digits, right? That's too much. You cannot compute those things. So how can one prescribe where to put the weights? So let's play the following game. Let me show you how to put a physical measure on a repellent periodic orbit. And it sounds weird because the orbit will be repellent, not attractant, but I'm going to put all of the limiting statistics there. And it's not that difficult. So we'll start with a special parameter in this family for which there will the third iterate will have the following property. So the third iterate will look like the Chebyshev polynomial. It will look like the parabola whose tip touches the top of the square. So there'll be an interval. So here's 1/2. It's a critical point. There'll be an interval for which the third iterate will look like this. So this is F3. Now, for this thing also, what's going to be true is that the second iterate, so if this interval, let me call it something, J. For the second iterate, there'll be an interval I whose image is J, somewhere to the right here. It just happens that way, you could check. Okay, so there is an interval here such that the second iterate is actually monotone, and I never remember which positive or negative slope. In my notes, it's negative, so let's believe me. And it goes like this. Okay, so this is F2. Yeah, of course. Yeah, of course. The third, yeah. The third iterate will have a lot of critical points, but this is somewhere near 1/2, right? So this is only part of the dynamics. This part of the dynamics is going to be enough, right? So for this map, what happens? The critical point, so this point is fixed under the third iterate, right? So the critical point will go to the left under the third iterate, then again under the third iterate, it will go to this point up, right? And it will be stuck there. And as I told you, the rest of the points will just follow the critical point. So everything will just be stuck there. Okay, on this period 3. Well, okay, this is really being recorded. This should be edited out. This is not true, but close. Okay, so here's the game I'm going to play. I'm going to push this down a little bit. I'm going to take a slightly larger value of the parameter. I'm going to miss. So I'm going to miss. So I'm going to take a slightly larger lambda. And now I miss. And instead of hitting here, I'm going to hit a little bit to the right. Now this point is repellent. It's a repellent periodic point for the third iterate. So it's repellent, and therefore, if I start taking the preimages of the interval I under the third iterate, I'm going to get a sequence of preimages. So I minus 1, I minus 2, etc., which converge to this point. So now here's my dynamics. I go left, right under the third iterate. I miss this point, and I march, but I get onto one of the red intervals. I march to the right, to the right, to the right. Now I get here. Now I have a complete freedom. This is smeared over the whole central interval, right? So for instance, I could take the image of this point and put it right at 1/2. That, by the way, if a critical point is periodic, that's it. It's super attractant. Everything converges there. SRB measure is the orbit of that point. But I don't want to do that. What I want is to tweak my parameter value so that I miss again. And instead of hitting here, I miss a little bit and I repeat the exercise. So again, I go here, here, then I miss, get into one of the red intervals and come out. Every time I'll miss closer and closer to this point. This is a simple continuity argument, intermediate value theorem. This really costs me nothing. And in the limit with this procedure, I'll get something which spends most of its time near this point. Almost all the time is spent trying to climb out from here. This point is repellent, but so what? Right? So I just put all of the SRB measure on the repellent period 3 orbit. But now you see there's too much freedom in here. I don't have to do it with 1 orbit. I could do it with 2. I could take a different repellent orbit. It will have a similar sequence of intervals convergent to it under some other inverse iterates, and I'll alternate between the 2. And then I'll put my SRB measure on the 2 of them. And by choosing how much time I spend at which one of them, I can assign whatever weights I want to them as long as they add to 1. And now I could do this with 10 orbits, and then I could do this with a Cantor set. But that's too much. Now you have the same freedom as arbitrarily define an accountable sequence of digits of a real number. That cannot be allowed. So, right? Okay, now I stop here. Thank you.
Totally random question.
Random questions are welcome. We'll average them and then we'll see.
So,
yeah.
I mean, at that point, you find is this Feigenbaum constant?
No. This is a different construction. This is a different construction. So Feigenbaum constants and such, the Feigenbaum construction does play a role in the story when we're looking at building attractors of arbitrarily high complexity. This construction is different. So the idea of this construction in a rather different setting goes back to a paper of Johnson from like late 1980s. This is an approach towards building SRB measures, right? In this family. Not proven an existential statement, but sort of building them by hand.
But you have a Carlo algorithm.
Mm-hmm.
Very hard to say whether it fails.
That's precisely right. And we probably know that there are some cases in which it's impossible, right? So in these cases, it will be impossible to say, and not just for Monte Carlo method, but for any method you use, but Monte Carlo for sure, okay?
I don't know what's about this now, but the algorithm that counted like the density of like the concurrent point. He's saying that if I left that running, every time I looked at it, it would be different and it never converges, or it'll converge to something and I just have no idea.
I don't know, it depends what you write. Depends what you write. So it's a valid question. Let me try to reformulate this, right? So it's a valid question to ask what actually happens in practice. So practitioners typically don't worry as much about the precision of computation, right? So they don't in practice worry as much about the precision that you need to take for the discretization and so on. So what you would do is you would just take some fixed round off. So you do like double precision, quadruple precision, and you calculate everything with quadruple precision. If it works, it works. So that corresponds to a model of computation. So people have looked at this. So for instance, a valid model of computation would be a computation with noise. So you treat the round off errors as added noise at each step, IID noise. So there is a paper of Braverman, Grigor, and Rojas, same Rojas, proven that in that model, basically there's always an SRB measure which is polytime computable. So the noise kills everything. So you will always have, at least in the mathematical model of that, you will always have a very plausible looking answer, right? Which in some cases provably wrong. in an interesting way. So yeah, so something like that. So this is somehow, these challenges are real in a sense, right? So, and when people do computations, they would tend not to notice this for also valid mathematical reasons. Sure. Yeah, so that's correct. It's not needed if lambda is computable, right? So in this scenario, it's not needed.
So without that oracle, I probably have something like measure. Strange. Only countably measured.
Yeah, so without, well, I mean, it's the same with computable reals, right? So, but it doesn't really make sense not to use an oracle for computing something about dynamical systems unless you could actually write, I mean, unless dynamical system is given to you in some computable way. Right, so this is what practitioners do. You have two options. You could either write a program which inputs the parameters. So for instance, this app for the Lorentz attractor that I showed you, that initially was written in such a way that you could put in the whatever parameters you want. The parameters were chosen to be the parameters that Lorentz used. Or you could just, if your parameters are computable, you could write them in. Sometimes it makes sense to do a computation for a specific map, in which case it would not be surprising. There are countably many inputs, so there have to be countably many answers, right? So if there is no oracle, you have countably many problems to solve, so there are only countably many answers to give, right? And I'm saying that some of these answers would not be computable. Well, I mean, if lambda is computable, you don't need a superpower.
Yeah.
Right? I mean, you don't need a superpower. Well, I mean, if lambda is computable, you're only looking at countably many maps, so countably many limiting statistics, right? So then it's a question about the countable set, and it will still have, but in general, if you look at the general lambda, even if you are given lambda, right? That doesn't somehow help in this case. Go ahead.
Sorry. So we want first
Mm-hmm.
So look was birds coming tens and tens, two-dimensional projection. But are they also tens?
Yes. So no, I mean, I'd say it's a good question, and it's a feature of this thing. So in that particular example, there is a limit for a typical, or so no matter where you click, if you assume that the click is, you know, IID distributed in that rectangle, the limit and shape will be the same. And it's some complicated limit and shape. It's complicated, and it's the support of the unique SRB measure in that case. That's a theorem. Incidentally, that theorem, so it's due to Warwick-Tucker, and it was proven with the use of computer. So it uses rigorous computer-assisted estimates. So computers are somehow used left and right in this subject. But yeah, so it's going to be the same shape. So they're all going to converge to the same shape. The shape itself is rather complicated, and that's the shape that you are seeing in the limit, right? And they converge both in the sense of measure and in topological sense. This is the set of limit points. Well, no, they're not dense in the plane. They become dense in some set, right? So they converge. The structure, yeah. So the structure of the invariant set is locally a counter set cross an integral. Mm-hmm. Oh, sure. Yeah, you could pick examples in which, well, okay. Yeah. All right. I'm getting a little ahead of it. So you can, right. So you kind of yes and no. So yes, in the sense that you could pick examples in which you have some finite or even infinite collection of attractant basins, right? And each basin will be just a collection of topological disks in the plane, and each one corresponds to its own SRB measure, which is just finitely supported on the attractant basin. These attractant basins don't necessarily have to be nice, right? They could be, even if there are examples, say when you have only two, so two SRB measures, but the basins are intertwined. So if you take an open set, you will have both of them with positive probability. So that's kind of weird, but could also happen. So it's a very, but it's a good picture also in a priori for Monte Carlo, right?
Well, let's thank Michael again.